Hello everyone. In this video we are going to look at the effects of dynamics of a brushed DC motor on the equations of motion for an N-link robotic arm. So if you remember in the previous video we derived the equation of motion for an N-link robotic arm if we add the effects of friction and the gearbox, right? So we added some terms here and changed the B coefficient, or added the friction that is viscous, added the friction that is Coulombic, and changed the D matrix into M matrix. Now, the fact is this T or tau, this torque that is coming from the motors here in this equation, it is generated by the internal dynamics of a DC motor. So if we want to bring that in, then our equations could be further modified, and the parameters of the DC motor electric circuit will be added to the equations of motion. So the torque that a motor generates on the rotor is proportional to the electric current passing through the circuit. So if you consider the electric circuit of a DC motor to be a resistor inductor circuit, right, RL circuit with a DC voltage source, V, then if the I is the electric current passing through the circuit, the torque generated on the rotor of the motor is a constant, which we call it the motor or torque constant, Ka, or some people might call it Kt, times I. So the more current you have inside the circuit, the bigger torque you can have at the rotor. Now, that's the first equation. Now, about the electric circuit of the motor, if you use the Kirchhoff voltage law, which is sum of the voltages or voltage drops across a loop is equal to 0. If you start here, so you have a V voltage, and then you here pass a resistor in the direction of the current. So this is going to be like V minus Ri, correct? Then you pass the inductor again in the direction of the current. So it's going to be the minus the voltage across inductor, which is LdI over dt. Right, and then what you have is an extra voltage generated on the rotor. That extra voltage is called back EMF voltage. Okay, and that back EMF voltage does depend on how fast the rotor is spinning. So if the rotational velocity of the shaft of the motor is theta dot, then you can multiply that angular velocity by a constant, which is called back EMF constant, or Kb. And Kb times that theta dot is the back EMF voltage, the voltage that is going to oppose your source voltage, correct? So you can say this minus this one is equal to 0. So this is writing the Kirchhoff voltage law in its original format. And now if you take all of these three negative terms to the right hand side, then you of course will get what? You get the equation that you see I wrote for you here. That's the other way. So this is coming directly from Kirchhoff voltage law. I don't want to get into details of the electric circuit, why the back EMF comes in, but that's due to the Lenz law, okay? Which is basically the current generated here is going to produce a voltage opposing the source voltage. So that's based on the Lenz law. You can study that yourself. But so this is the dynamics of the electric circuit. That is the torque generated. And as I said, the back EMF is just a constant times angular velocity. So now we can combine these two equations into my original equation that I have from previous lecture and get into more basically detailed equations of motion, where the input to a robot is really the voltage that you apply to your joints, and the outputs are basically the q double dot terms, right? And then of course integral of them will be q dot and q. So the input to a robot is not really the torque, because you don't drive your motors by giving them a torque. Torque is the output to the motor. The input to the motor is a voltage, right? So this is our ultimate goal of this lecture. We pass the V, and it gives me back the Q double dots, right? And here we have to include this equation, as I said, plus these two. So before I get into development of that, let me mention one thing for you here, and that is the torque versus speed curve of a DC motor, brush DC motor. And you know, DC motors have brush, brushless, and so on. Here is the brush one, the one that has the commutator to reverse the direction of the voltage on the rotor, so it can keep spinning in the same direction. Again, I don't want to make this an electric circuit course. But if you see here in this graph, it says for any specific voltage, the relation between the torque and the RPM on the shaft of a motor is a linear relation, but with a negative slope. So basically, the faster the shaft rotates, the smaller the torque it has to give to the robot for motion of the members. Or if the members are heavier, you need more torque to move them. It definitely means you can rotate the members at a slower speed. Now, of course, you know why? Because the power, right, on the motor shaft is tau times omega, right? And this power is limited as long as the energy that you get through voltage is limited. Because once you have a voltage, a fixed voltage, you are injecting a fixed amount of power into the system. So this power out that you have here is also going to be constant, and constant means if tau goes up, omega has to go down, or vice versa. The other way you can look at it is through this equation of electric circuit. If you look at the equation of the electric circuit here, this one, we can also see this relation. How? Well, in most of the cases, in most of the circuits, this induction amount in the circuit is very, very small compared to R, compared to anything else. So in many practical applications, including what we are going to do in a minute to derive the equation of motion, we neglect L, right? And I mentioned that for you here, that in many cases, we just neglect the inductance. That takes care of this extra derivative. And now the relation looks like a linear relation. Now, this V is what I want to keep constants for that graph. Ri, well, I here from the bottom equation, if you look at it, I is clearly the torque divided by the torque constant. So if I plug that into the top equation, it becomes V equals R over Ka, a constant, times tau, and then plus Kb times theta dot or omega. So this is what you will get. And if you look at this equation, clearly that explains that graph, right? Because if V is constant, then you can take one of these terms to the other side, and that term becomes negative, which clearly explains that negative slope, right? So if I bring it down here, it becomes, let's say I want tau versus omega, it becomes tau is equal to Ka over R times V, and then minus Ka times Kb over R times omega. So you clearly see why the relation between tau and omega is a linear relation with a negative slope. that's the slope. And this term, because v is constant, this term is simply going to be a constant term. So it is like a minus b times omega, which is exactly this line here. Okay, so that is justified as long as we say the induction in the circuit is very small, which, as I said, for many practical applications it is. Now, I want to also mention a couple of technical terms that you hear a lot here and there about the DC motor, and that is the stall torque and the no-load speed. So the stall torque is where the motor stops rotating. Why? Because the link that you want the motor to turn is so heavy, or there is so much force on it, that the motor is not capable of moving it. In that case, omega of the motor comes all the way to the zero. It cannot spin, and that is where the motor gives you the maximum torque it can, although still might not be enough to turn the system, right? Because this guy is less than the tau that you need from the load. But this maximum torque that the motor gives you is what we call the stall torque. And stall means, as I said, no rotation. The other case is when there is no load on the motor. So the motor can rotate freely. When the motor can rotate freely, it means the torque goes all the way down to zero. And that's where your rotor of the DC motor can spin the fastest. And that fastest RPM is what we call the no-load speed. Right? So these are like the X and the Y intercept of the tau versus omega curve. Right? X-intercept is no-load speed, Y-intercept is like the stall torque. Now, in reality, when we use motors, we do not run it under any of these conditions. Because when the motor is attached to a link, there is definitely always some load. Even if the link is not supposed to, that link of the robot is not supposed to move something, still it has gravity. And still there is what? There is definitely some torque that you need at the joint to keep the gravity. And if you remember that static torque, that tau is what? It's J transpose times F. Right? Where F here is the force of gravity only. So if you multiply the transpose of Jacobian by F, that is the torque at the joints to just keep the robot upright and to compensate for gravity. So you always at least need this much of load on the joints, on the motors, so you really never run in the area of zero torque. Right? On the other hand, you do not want to drive a motor very close to the stall torque, because the more torque that you expect from the motor means what? If you look at the equation of the torque, more torque means what? Means more current. And the more current you try to get out of this electric circuit, if you don't pay attention, you can easily burn the electric components and basically make the electric circuit dysfunctional. There is some maximum current that you can get out of that circuit. So you really do not want to, in this range, you do not want to go all the way up to the low torque. You do not go all the way to, you cannot go all the way to zero torque. In reality, you have to work somewhere here in between. And for many of these motors, there is another thing called rated torque and rated speed. And these are the speed and the torque points that the manufacturer thinks that gives you the best efficiency of the system. So it is a point here. Maybe if I go and look at this curve, it might be some point here in the middle, or maybe a little bit closer to the stall torque, right? And this point is the point that the manufacturer thinks you should operate the motor at. Now you might say, well, This here gives me, let's say if it's this point here, this gives me 1,000 RPM, which I do not need. What should I do? Then you definitely need to have a good gearbox to go with it. If the RPM that you need is 100 RPM and the rated speed of this motor is 1,000 RPM, you definitely need to use a gearbox that has a gear reduction of 10. Okay, and I'll show you that in the data sheets of a DC motor. I'll show you where to find this data. All of the numbers that I have mentioned here, KA, KB, R, L, right? The stall torque, the no load speed, the rated torque and speed. So, but again, as I said, these rated ones are the ones that the manufacturer is suggesting you operate the motor at. Good. So now, with all that, let's go and finalize the derivation of the equations of motion, and then we go over the DC motor data sheet, some samples. So this is the equation that I derived last time, equation of motion of the robot in the joint space with friction and gearbox effects added. This is the equation of motion, the equation of electric circuit, Kirchhoff voltage law. And as I said, for many practical applications, we neglect the inductance terms, so we really use this equation, equation 2. Then, of course, the torque at the motor is the torque constant times electric current in that circuit, so this is equation number 3, right? Because that gives me that tau that I need here. And definitely the Q dot M that you need here is R times Q dot L. Because here, remember, this back EMF is what? Is a constant KB times theta dot, but which theta dot? Definitely theta dot of the shaft of the motor. But if you remember our equations here, when I say Q dot, this Q dot is Q dot of the link, not the motor. So if I want to add that here, this term, if I want to convert Q dot M to Q dot L so everything can be mixed together, I have to consider the fact that Q dot M is R times Q dot L. So this one goes here. This one, as I said, goes here for the torque. And then in equation number 2, what we will do is we'll try to combine 2, 3, and 4 together to find torque as a function of voltage. Because it's very easy, right? If I want to, I can find torque as a function of voltage. How? Well, torque is K times I if I can find I from equation 2, because clearly from equation 2, my I is what? My I is V minus KB times Q dot M, the whole thing divided by R. Right? So I plug that I into the torque equation. So definitely my torque, which is Ka times I, it is going to be Ka over R times V, then minus Kb over R, and then for this Q dot M, I plug in R times Q dot L, and that adds an extra R for me here, and then Q dot L. So this is what you can see in that equation, right? And then once I have this torque, I'm going to plug this 5 into 1 and get rid of the torque. If you do so, you are going to get this bottom equation here, this one, the top equation in this inside the red box. In this equation, this is the electromechanical model of a robot driven by brushed DC motors. Your MQ dot, double dot is the same. The centripetal and Coriolis terms are the same, composed of Christoffel symbols. The static friction, the viscous friction, right? There is one term now that you have to add to the viscous friction, and that is the back EMF friction, right? And that's what you can see here. that is coming from this term, because there is something in the torques that needs basically it has a connection with Q dot L, and this term here, this diagonal term, is entirely multiplied by Q dot. So that negative term that comes here on the right hand side, I take it to the left hand side, it becomes positive like this. And if you look at the coefficients, you clearly can see them here, right? This one, by the way, also needs a Ka. You have a Ka Kb R over R, which you can see here, Ka Kb R over R, and then there eta times R extra in this equation, right? Because you see the R is R squared and there is eta. And where is that extra R and extra eta come from? Clearly from this equation. Because the torque that you plug in into the original equation of motion, those torques are all multiplied by R eta. So that R eta extra comes in aligned with this coefficient multiplied and give you that extra linear term that you see in the equation of motion. The effect of gravity is the same. And now in the right hand side, the diagonal R eta term, now what you need is to keep the V term. So the coefficient that you have is 1 R eta, and here the coefficient of V that you have is KAR. So Ka over R and eta are multiplied all together and give you this term, and then times the voltage. Okay, so now if you look at this equation of motion on the top line, what is it? That gives you the equation of motion of the N-link robot, but the inputs to your equations are the voltages that you pass to the motors, not the torques, because the torques are the results of applying voltages. So this equation that you see on the top, that is the most complete equation we have derived so far for N-link robots in the joint space, by adding the effects of friction, the effect of gearbox, and the dynamics of the DC motor. Where again, the definition of the M matrix is the same as the previous video, and the definitions of the B total, the mu total, and the I total. So this is the most complete set of equations we have derived, and if you see, there are a bunch of parameters that you ought to know if you want to model the equations of motion of the robot. What are they? You need to know the static coefficient of friction for each link, for each shaft of the motor, the viscous damping coefficients for the link shafts and the motor shafts, the inertia for the link, the inertia for the motor shafts, the gearbox speed ratios, the gearbox efficiencies, the torque constants, the resistance in the circuit of DC motor, the back EMF constant in the circuit of the motor, the mass of each link, the components of the Jacobian for linear and angular velocity, and finally Ri. This Ri is a different thing than this R. This R is the resistance, this Ri is the rotation matrix. So here I just want to emphasize that we have two R's. One of them has a subscript, the other one doesn't, and the one that does, it is a rotation matrix for link I. So you see there are a ton of parameters that you ought to know, and once we know them, we can simulate this the most complete equation that we have driven so far. Now, where do we get them? Well, the rotation matrix comes from the current configuration of each link, so it is a function of Q. So this gets updated in at each point. When the Q changes, this guy does change. The same thing with JV and J omega. J matrix in general is a function of Q, so when Q changes, then so JV and J omega. So these guys are all functions of Q. The configuration of the robot does change these guys. The mass is constant for each link. Then the gearbox reduction, the efficiency of the gearbox, the back EMF constant, the torque constant, the resistance, right? And the inertia of the shaft of the motor, these guys, as well as the friction terms, all of these let me show you all of them. All of these 8 parameters, they come from the DC motor spec sheet. Or at least most of them do. Maybe the frictional terms are not easy, but most other parameters, they come from DC motor data sheets. And then what? You have the mass of the links, you have the inertia of the links that you can basically get from the design of the robot, and then the frictional terms on the links should also come from, again, the robot. So this term, this I, and this M. These 4 terms also come from your robots. Correct? So once you know your robot, once you know your DC motor and the gearbox of it and everything, and once you know the configuration of the robot, at each point you can determine each and every one of these parameters. As you can see, there are a ton of parameters here, right? So 3, 6, 9, 12, and 15. There are 15 parameters, and they're almost all, each one for a link or a motor. So if your robot has 6 joints or 6 links, you have 6 times 15, which is 90 parameters. If you want to simulate the equation of motion for a 6 degree of freedom robot in its entirely without neglecting anything, you need to know about 19 parameters. So in general, this is like what? This is like n times 15 parameters. That you need to know. Although JV and J omega and RI, you just need to know them once, and they just do change as functions of Q, but you have to recalculate and update them. So now let's look at the data sheet of a DC motor. So this is a DC motor from the company Amtech Pittman. And this DC motor is a DC054B series. So I took this data sheet from that company. So the credit all goes to the company for providing these spec sheets to the users. And as you can see here, you can give these motors up to 80 voltage DC, and they can rotate up to 6,000 RPMs. Clearly, you never need in a robot motion as fast as 6,000 RPM. That's very, very fast, right? So you definitely need to bring down the RPM. As you can see here, they do have encoders, they do have brakes, they do have different options for gearbox and so on. There is no mention here of the Hall effect sensor or tachometer. So all you can get out of these motors is really their angle. You cannot get their angular velocities, at least with the current configuration, unless you add that to the top of the motor. So now what do we have in this motor? If you go and look at the parameters, you have a maximum voltage that I just read for you. This is the maximum voltage that you're allowed to apply, 680 volts, no more than that. This is the maximum speed that you can get, although in reality you should not go to that 6,000 RPM. And you might say, well, what is the rated speed that I'm supposed to really use these motors at? Is that below 6,000? So if you go down here, you see that when it goes to rated voltage, also you have a rated voltage, a voltage that the manufacturer is expecting you to apply, not 80 volts, is one option is 12 volts. If you want to go at 12 volts, and that's called rated voltage 1. The other that it suggests is 15.2, correct? And there are only two rated voltages that the manufacturer suggests. And then you see for 12 volts, the maximum speed is 3680 RPM, and for the 15 volts is 5250. Definitely, the bigger the voltage, the bigger the rated speed or no load speed, and you can see that from these curves, right? As you can see, when the voltage is increasing, then so your omega max is increasing, your omega nominal or rated is increasing, your tau max is increasing, and so on. Because more voltage means more power into the system, so you should expect to get what? More power out of the system, and more power means bigger torque or bigger omega or both. So definitely more voltage is an option if you want to go higher torque or higher RPM, and it gives you two options. So again, you can go up to 80 volts, but by no means the manufacturer is suggesting you to use it. It says go either with 12 volts or 15.2. That's why you see a rated voltage, an RPM, and a rated torque. You see, at that voltage, it is giving you a 6.9 ounce-inch torque, right? And at second voltage, it is giving you basically, let's see here, 4.7. This is what the manufacturer is suggesting to use. So use this combination if you want for the second voltage, or use this combination for the first voltage. Clearly, you see the first combination gives you more torque, lower RPM. The second one gives you, or suggests, gives you less torque, more RPM. And definitely the product of these two terms are not going to be the same because the voltages are not the same. So this is those guys. Now, if I go back here, what other parameters can I find in the spec sheet? So I have the stall torque here also. This is the torque that is maximum you can expect to get out, 10 ounce-inches. Of course, you see both of these numbers I showed you were below 10. One of them is 6.9, the other one is 4.7. So although you can go up to 10, but that's where the motor stops rotating, and that's where you are taking too much juice out of the wires that you are going to burn the wires soon. So you should not count on 10 ounce-inch of torque out of this motor. Then you have the Coulombic friction torque, tau F. So it directly gave you the Coulombic friction torque, right? So it directly gave you the mu s, right, times N times R. So it gave you the whole torque due to Coulombic friction. It also gives you the viscous damping factor, the B's. This is B of the motor, right? What else does it give you? It gives you the rotor inertia, I, correct? So this is like your IM in that notation. This guy here is like your BM. This guy here is the total mu S times sine times everything, right? And then you have all of these other things. It also gives you some information about thermal analysis of the motor, because that's important, right? Here we don't discuss it, but really you have to make sure the amount of heat that is generated in the wires are dissipated properly and you're not overheating your motor. It also gives you in grams. The mass of the motor is 590 grams. Incorrectly, it is called weight. It is mass, really. Then what else would you see? You see the torque constant, Ka, is provided. The voltage constant, which is really the back EMF constant here. So this is like your Ka. This is like your KB. Then you have the terminal resistance and inductance. So you have your R and L here. Now L is not, you might say, well, that's 0.63, the R is 0.72. These numbers are close. Why should I neglect L? The matter of fact is this. If you look, the inductance is millihenries. So it's not really 0.63, it's 0.63 times 10 to the negative 3. That's why you see L is much, much smaller. It's like 1,000 times smaller than R. So that's why in many applications you can, as I said, simply neglect the inductance. And all of these numbers that this data sheet is giving you are measured at 25 degrees Celsius ambient, so at room temperature, or a little bit more than room temperature. If you keep running these motors and the heat dissipation is not well, and the motors get hotter and hotter, then do not count on these numbers to be exactly there. They would definitely change. I mean, some of them would definitely change. Maybe the inertia does not change significantly, right? Unless it's superheat and the expansion is big, but you can count on your resistance to change a little bit, or the torque constant, or any other thing. This is the graph that I mentioned for you. This is the graph of speed versus torque instead of torque versus speed. So it's omega versus t, but again, or tau, but again, you expect the graph to be aligned with negative slope, as you can clearly see here. And finally, if you go down, it talks about the gearbox now. So here you have the gearbox. It gives you exact ratio, which is R here, and it also gives you the efficiency, or eta. Okay, so you see most of these parameters that you wanted in the equations that we mentioned, they are all or mostly given to you, correct? So if I go back here, which one of these did you see in the spec sheet? If we want to recapitulate before we finish up the video, this data sheet gave you mu, or mu of m actually. It gave you this one, it gave you b, it gave you I, it gave you R, eta, Ka, R, Kb, and L. If there is any L here, there is no mention of L, but there is also L. It gave you L, right? So it gave you everything literally that you wanted for the motor. And once you know the data from the robot and the links, which is M, I, B, and mu, and these guys are also again coming from your robot geometry, then you can definitely simulate the motion of this system entirely. And one last thing, if you look at this gearbox, the ratio here of R here is 230 to 39, or 5.9 to 1. So that's another thing you have to pay attention to, is most of the time these R numbers are not really integer numbers like 10 or 20. Most of the time they have fractions. If 5.9 is not enough for your application, you need more torque and a smaller RPM, then you can go with the second gearbox option, right? Use the second gearbox that can work with this motor, and use 11.5. If that doesn't work, go to 19.7, or go to what? Go to 38, go to 65, and then there is even more. You can go all the way to as low as basically 4,700. So this is a huge amount of reduction here. This is your R, and if you square that number, 5,000, just imagine how big that number is. And that is what I mentioned in my previous video, that under extreme cases where R squared is a very, very large number, then when you look at your M matrix compared to the D matrix, your M matrix can be almost what? Completely diagonal. Because once R instead of 10 or 100 is 4,000, then you can imagine how big this number is going to be compared to this number here. And it makes it completely what? Diagonal and decoupled. So I hope this video was useful to you and gave you the kind of good overview of the electromechanical model of an N-link robot in the joint space given a brushed DC motor. So thank you so much for your attention. I will see you in my next video.